Well, free food. Well, you pay tuition.
Okay, that makes sense. Thank you.
Go ahead. We also have drink. Help yourself. All right. So, I always imagine, like, for the last lecture or the last meeting between us, um, should be something like a concert, like the one that I just played, because it should be a moment that people feel excited about. I feel excited about. You feel excited about that. Oh, finally, I get rid of this guy. And for me, it's like, finally, I'm done with you guys, right? No, I'm just kidding. But the thing is that I never get a chance to have lectures in like the night, and I don't want to do that in the night. So it won't be a concert like that. Plus, the school never provide us a good environment like that. Question? Not this time. But traditionally, one thing I have been kept doing is actually the pizza. If you don't, if you don't believe me, check all the slides that I published in the last lecture. It's typically like a pizza party after finals. But this year, since we have done things differently, like we offload the final exam to Triton Testing Center. So it's better for you, better for me, because you guys have more flexibility. And typically the time that the school schedule for us is terrible. Like this time is Saturday, right? Do you want to be here on Saturday? No, neither am I, right? So the thing is that, okay, let's do it here. And we still want to have the pizza. So help yourself. And I hope I won't see them because every time when I do it after the final, people just like, I don't want to see you anymore. So they just left the classroom and they don't want to see me. So I still have a lot of it left over. The worst scenario, it took me like 3 days to finish all of them. And I hate pizza for another year until I have this summer. Well, another summer session, right? But today we are going to have a final review on what we have learned. So the reason why we want to have a final review in addition to the ones that we taught, because sometimes we really need a different angle of seeing things. I don't know what you like, but I'm a person, well, in addition to some of my nerdy hobby that you guys already know, I also like travels. One of the countries I like to visit all the time is Japan because one of the reasons is probably because 25% of my heritage comes from Japan. But also, I really like that country in a way that nobody really knows me there. It's a place that I can speak the language, so it's pretty much like a place that I can isolate from all my work, but also enjoy the life there. Help yourself with pizza, and for every Japanese people, like Fuji Mountain is one of the ones that people want to visit at least once in their life. I hope I can visit that once in my life. And but most of the people they see Fuji Mountain in this way. They hope it's not cloudy. However, if this is Mountain Fuji, if you view it on an airplane, and this is indeed what I took when I had a flight flying over there. So you will see that, okay, don't worry about the cloud because you are actually above that, right? And another example is Mount Rainier. If you are from Seattle area, like everyone is hoping to see Mount Rainier, and because it's so rainy there, so a lot of people are saying that, oh, if you see Mount Rainier today, then you are in good luck, right? However, if you could take a flight, even though it's cloudy below, you will still see Mount Rainier clearly. So what does that mean is that sometimes if you're confused about a problem, we have to think about if there is a different angle of seeing that. Like if you feel a lot of things are confused, then don't hurt to start from the high-level perspective and review the problem again. And today is the time we are going to see computer architecture in a different way. So if we want to take a 10,000 feet view of the whole computer architecture, it's basically this model. It's the von Neumann architecture. All the problems, all the reason why we are doing this, all the reason why we calculate things in this way, all come from the fact we have a von Neumann architecture. And the basic idea of von Neumann architecture, as we have been mentioned several times, is that if we want to execute a program, it requires the program to be represented in instructions that the machine or say the processor can understand natively and encode them in a data format like binary, or even with binary there are big endian, little endian, and ASCII code, this kind of encoding of your data to let a computer understand what I'm processing. And whenever after I got this being encoded in a way that a computer can understand, we will store them in a storage first or somewhere in a memory. And when we need to run this program, when we want to use those data or whatever you want the computer to process for you, everything has to be in the memory, no matter where it was originally. If it was in the network, load it from the network to the main memory. So before anything comes into the memory, nothing can happen. And then after that, what happened is that your processor would use its hardware unit to figure out what to execute and what operation should we be doing. So to know like what to execute, there are several things that we need to know. First of all, where is that specific instruction? So that's why we need a program counter. We need instruction fetch, and when we fetch, it comes from memory, and then to figure out what functional units we need to finish the task, we need to decode, we need to prepare the operands in the register, and then you have the functional unit to perform the corresponding operations. And once you have the result, you have to present it in a register file so that later instruction can use it. And once you are done with an instruction, you would either advance the program counter to the next instruction or use a branch instruction to decide where to go. So that's pretty much the von Neumann architecture. And why is it the most high-level overview of a computer is because with this architecture, by putting different instruction streams and data inside our computer, you can actually let the computer perform a completely different task without having it being hardware reconfigured. So that's the reason why we want to use the von Neumann architecture. And based on that, you can easily imagine if I want to evaluate the execution time of running a program on this von Neumann architecture, it typically would involve how long do we need for each instruction to be executed on average, and how many instruction instances that we need to execute. And for each instruction instance we need to execute, it contains two factors. One is how many cycles on average for each instruction, and how many seconds on average for a cycle. And first, also, don't forget we need to consider the instruction instances. So that's why we have this formula, IC times CPI times CT. So even though you have a program looks like this, which only have like 11 instructions for 12 instructions for this example, but don't forget, some of them we only execute them once. Some of them we do execute them several times. So for example, like if we have to execute this 5 instructions for 1024 times, then your instruction count will have to be this 7 instruction plan plus 5 times 1024. And on average, you can estimate the CPI pretty much as 1.8 based on the data provided. And that's how we get the roughly runtime. And you would get a rough performance. Oh, okay, it takes this amount of time, right? So, but then the thing is that as a computer architect, as a computer scientist, our goal is that we want to make our program faster. So how do we make our program faster? Of course, then if the best scenario is that we should let all 3 factors on the right-hand side lower. So for example, some people would argue x86 is never a good idea in instruction set architecture design. But since the lecture yesterday, when we talk about domain-specific architecture, if we can let the execution of an instruction, an accelerated complex instruction really fast, it doesn't hurt that we make the instruction more complex to make the instruction count lower, even though the cycle time goes up, right? So the thing is that the execution time, or say the performance in general, is a synthetic effect of all 3 factors. Although we always want these 3 to be always low, but it's almost impossible to get all of the benefits. So how to lower the cycle time? So from what we have learned before, as a programmer, you can ensure your processor to be at the reasonable cycle time. So for example, we have learned that our processor has dynamic frequency scaling to save power, right? So sometimes if you don't do anything specifically, that would let the operating system and the hardware itself set the frequency. So if you have a job that you really need very short latency, and if you want to guarantee that it has to be finished at a certain period of time, then you have to explicitly set the frequency yourself. And if you want to lower the instruction count, several things that we have been doing. So for example, we have told you that, well, you can implement algorithms more efficiently from using a more compact set of statements. And you can also try to use like instructions that would encourage the compiler to generate vector instructions, spatialized instructions. Or so the thing is that as a programmer, there are many things that the compiler won't do for you. And I have provided quite a few examples to tell you if you don't do this, the compiler won't do, right? So that's a way that you can reduce the instruction count. And again, for compiler, several standardized optimization they would apply to lower the instruction count. So for example, function inlining to avoid the code overhead, which you already learned in assignment 3, and loop unrolling, which we have been talking about after the control hazard, that we say, well, instead of doing branch prediction, what if we can get rid of all the branch so we don't even have to worry about the loop control overhead, as well as the potential of branch misprediction, right? And another one which another set which you also learned from assignment 3 is assignment 4 is some of the common set of compiler optimization, like common sub-expression elimination, constant propagation, code motion. However, this compiler optimization, it used to work very well when we are at a single-threaded version. However, later on we learned if we move things to multi-threaded program, this compiler optimization may cause our program to be more functioning. So for example, the common sub-expression elimination and constant propagation are the reasons why one of our demo program wasn't able to stop because it constant propagate the fact that some constant variable should be 1 always and never receive the update from another thread, which cause an infinite loop, right? So, and again, lower the instruction count doesn't always guarantee we are going to have lower execution time. So we have shown you that in a poorly written loop addition example, that our array addition example, we are seeing the execution time goes up, even the compiler significantly reduce the instruction count. So another main factor that we have played a lot to reduce is actually the CPI. So And a lot of our stuff, we are talking about how to reduce the CPI. So for example, if we could have make the cache hit rate higher, that's actually making the memory access CPI lower, right? So it's actually a way to reduce the CPI. And when we talk about instruction level parallelism, for example, auto order execution is basically trying to hide the latency of a long or a long latency instruction with more instructions covered, right? So in that way, we are also reduce the average cycle time. And if you are able to do superscalar, which make multiple instructions executing at the same time, that's also reducing the average cycle per instruction. And also like branch prediction, because we are scheduling instructions ahead of time to cover the long latency of branch resolution. So it's also improving the instruction level parallelism as well as CPI. And so those are the stuff that the hardware side have tried. And on the software side, you can actually try to reduce the data dependencies. You can actually try to make your code behavior more predictable. So then we can increase, by reducing the data dependency, it means that we are increasing the chance of auto order scheduling and making the code behavior more predictable. We are actually making branch predictor easier to predict. And also, again, for compiler, they can do things to optimize for CPI. However, for the compiler, they have very limited scope. For example, they can only work on a basic block label, which they cannot go beyond the function level. So you have more freedom to do things. And so those are the optimization that we have learned. On the other hand, if we want to figure out where's the performance bottleneck or which part worth more for us to investigate, or what's the maximum potential of doing something, then MDOSL becomes really important. So MDOSL is formed, as we mentioned, it has nothing different from the speed up equation that has been given. However, there are several insights that we can get from MDOSL. For example, if I want to evaluate the maximum speed up of doing something, that's corollary 1 here. If you want to know what to work on, find out the part that spends the most amount of time, that's corollary 2. And the corollary 3 tells you that after you optimize something, then there will be a new bottleneck coming up. Like in the hardware accelerator we demonstrated yesterday, once we make the computation super fast, then the problem goes back to the memory again, right? So that's why modern hardware accelerators, they typically have a large array of memory on chip, because once you make the computation super fast, memory problem emerges again. And and a lot of people were talking about, should we parallelize something or not, right? And here's the thing, corollary 4 tells you exploiting more parallelism is probably the key to performance gain in machine architectures in the future, because the serial part is not improving at all due to the limitation of Moore's law and Donadian scaling, right? So then it becomes really important that in the future, we are trying to design algorithms that can help parallelize as many parts in your program as possible. And however, there are always problems that we cannot parallelize it, and there is always a bottleneck that's serialized. So then single thread performance is still important. And in fact, again, thinking about the moving target, once we fully optimize the parallelizable part, then the serialized part becomes a problem. So for example, well, what if like NVIDIA is really like getting some help from like aliens, and they are able to produce a processor with 100,000 cores, and then a parallel architecture or parallel GPU is never a problem. Then the problem still goes back to how can we make each single thread microarchitecture faster to make the program faster, right? So that's why I always say Intel has a future, because eventually there are still parts of your program that can never be parallelized. So that's when we need single thread performance to be better. However, the corollary 6, which is not something we talk about in detail in this class, is that, but it's very important, is that don't hurt the most common case, don't hurt the uncommon case too much. So for example, like for the most common case, we keep optimizing it. However, some of the optimization, it comes with an overhead. So for example, if it will cause the serialized part to be slower, then we don't want to do it, right? So for example, when you use GPU, it always comes with the overhead of data movement, which is serialized. So that's actually hurting the serialized part. So that's why in many cases, we won't see GPU give you a speed up because that part is actually going bad. So talking about what's the most common case scenario that we should optimize in a computer system, it's actually, if you look at the technology, that's the memory, right? So the reason is because there are several reasons on the technology side. So Moore's law, right? By default, if you remember what's the definition of Moore's law, it's only talking about the density of the chip, right? So with the density of the chip, you can make a transistor smaller, and if it's the regular transistor, then or a switch, then you can basically make the speed of the transistor switching faster because the wire length is smaller now, right? Because that's completely the propagation delay problem. However, if you consider memory, for example, like DRAM technology, that is based on capacitance. And if you could remind yourself about the physics class that you learned as a freshman or in high school, the characteristic of an RC curve is not a linear curve. What does that mean is that it's slowing down at the very end, right? So if you remember that curve. So what does that mean is that the performance of your capacitance does not scale with the size of the transistor itself. So what does that mean is that even though I can make the transistor smaller, the speed of fully charged that capacitance is actually not going to improve a lot. So that's why we have this gap between the regular transistor-based processor and capacitance-based DRAM. So definitely a good way to think about that is what if I can use faster technology? However, if you could have think about so first of all, right? So like right now, because of the memory technology and the processor speed has a 50 times gap. And thinking about when we are executing instructions, there are two stages that we typically would need with access memory, right? So based on our earlier calculation, this would account for 99% of the time. So that's definitely one of the problems that we have to address. So we have been mentioning, well, if we want, because the DRAM is a capacitance-based technology, so if we could replace that capacitance-based technology with transistor-based, latch-based storage, which is like SRAM, that would solve the problem. But don't forget, SRAM, it takes 6 times of area than the DRAM. So that's why it's so expensive. So it turns out the intermediate solution that we did is that we make smaller cache in between the processor core and the DRAM. So typically in your processor, your cycle time is less than a nanosecond, and the SRAM is probably about a nanosecond or at most a few nanoseconds. So depending on the size of the SRAM, because when the SRAM goes bigger, the access time is also larger. So that's why we cannot make, one of the reasons we cannot make L1 cache really big, because the access time is going to be long anyway. And for DRAM, if you are lucky that you don't have to fetch another page, it would take tens of nanoseconds. However, if you need a fresh new page to be latched in the row buffer, that would take around 100 nanoseconds. But in general, it's going to be tens of nanoseconds to 100 nanoseconds in terms of the access time. And for your storage, depending on the technology that you have, it's typically tens of microseconds than the nanosecond scale. So those are the numbers that you should have in mind. And but the question to us is that how does adding that small cache would help us in performance? And the answer is that it would help because our code is basically very predictable. So if you pay attention to these pieces of code, each statement in serial, they would go one after another. So that's so-called spatial locality, right? And if you talk about the loop structure, you are reusing the same statement again and again. So that's called temporal locality. In terms of the data, for this array, we are visiting the next item after we visit one. So that's how spatial locality shows. And then we would repeatedly use this output array as well as the vector again and again. That's why we would see temporal locality comes into play. So with the addition of cache, this is how we would actually use memory for now. So in theory, if you do things right, the processor should never talk to the DRAM. The processor should never talk to the DRAM. Don't forget that. Processor never talks to the DRAM in modern architecture. It always talks to the cache. If I am accessing instruction, it comes from the instruction cache. If I'm accessing data, it comes from the data cache. And only if we cannot find stuff in the cache, it's the cache's responsibility or the memory controller's responsibility to sort it out. And what that would do is that it would go down a lower level memory hierarchy to find the block you want. So again, the basic unit of cache in management is always a block. It returns a word to the processor, but whenever it wants to get stuff in, it's always block by block. So whenever you want to attach a state, it's a block. Whenever you want to update data, it's by a block. Whenever you want to kick out, it's a block. Whenever you want to write back, it's a block. So in our policy nowadays, every processor is typically using a write back cache. By write back, it means that when we have an update, we don't present that update all the way to the memory DRAM, but instead we only do the update at the closest cache has the data. So what does that mean is that it would guarantee that a write operation won't take forever to finish so that your processor can continue working on. However, it also comes with the cost is that if we don't manage the cache carefully in a way that whenever you want to discard something, you always have to write stuff back to ensure other people has it. So this is the basic guideline and the flow of how that works. So now, as a software programmer, it's very important for you to figure out how to write cache-friendly code. And here is some of the tips that I can give you regarding how to write cache-friendly code. So first of all, a lot of people would think instruction is an issue. But to be honest, instruction is less of an issue unless you have too many branches. So, and the reason is because instructions are typically pretty small, and our instruction cache is big enough to capture a lot of them. And so most of the time, that's why during the class, we seldom talk about optimizing for instruction cache. Instead, we talk about optimizing for data accesses. And for data accesses, here's the guideline. First of all, you want to know if my code is really performing well. So here are the steps that operationally would be useful when you are solving a performance evaluation problem for your code on the cache in a way. First of all, don't forget to use the geometry of your cache using C equal to ABS. And then list the sequence of memory addresses that your program would access. And then partition each address based on the geometry of the cache, and then simulate the cache to see if there is a hit or miss. So if you have experience of taking the midterm, you should know that we already try to guide you through that process. And we will do the same this time in the final, that we will give you a code. We will ask you to write a sequence of address. We will ask you the geometry. So hopefully this time you will get the result better. And then once I figure out my cache performance, once I figure out it's going well, then there's nothing really I need to do. But if it doesn't go well, then there are several things we have to think about. First of all, we need to figure out how come we have that problem, right? So then there are three sources of cache misses in a single threaded setting. That is compulsory miss, the miss due to the first time access of a block, right? And the second thing is the conflict misses the miss due to insufficient blocks of the target set. So, and finally, capacity miss, the miss due to the insufficient space, total space in a cache. So those are three main reasons. And typically, my guideline of telling you how to identify the source of cache misses is probably easier to come with the compulsory misses first, and then see if it's a capacity misses, and if it's not neither two, then it's going to be the conflict misses. So this is the idea of C equal to ABS, and here's the thing, right? So if you want to partition an address, it's basically better to partition it into the binary. However, I know you guys don't have a lot of time, a lot of tool in the Triton Testing Center. So in your test, we would typically make the partition aligned with hexadecimal. So what does that mean is that if you, well, I can give you a hint, right? If you calculate the geometry, if you tell you the number of bits in your block offset is not something multiplied of 4, you got it wrong, right? If your index bits is not something a multiply of 4, you got it wrong, right? So this is a hint that I can give you, right? So the thing is that, okay, so for each hexadecimal, it represents 4 digits in binary. So that's why I'm saying if it's a multiplier of 4, that makes you guys easier to partition it. So, and how to partition it? You should use C equal to ABS formula, and we would have several parameters that you have to use. The C represents for the total capacity in your data array, and the A stands for the associativity. And associativity, typically, if it's n-way set associativity, we would use that n as the A. However, there is a spatial jargon called direct map. It actually means one way. So if you see direct map, don't be panicked. It means 1. And the block size in bytes actually means the B. And I don't know why, but a lot of people still want to call it cache line. So if you see some people say cache line, that means the block size. And again, a lot of the problems that I put in the final or in your midterm is basically shared among the UCSD faculty of teaching who teaches UCSD CSE142. So some other professor, they would use the jargon of cache line. So that's why you still see cache line. If I can control everything, I would do block forever. But if you see cache line, that means the block size. And number of sets is typically an unknown that you have to figure that out. And in fact, most of the profiling tool, they won't tell you this. And then once you figure out CABS, you can use log B to figure out number of bits in your block offset, log S to figure out the number of bits in your set index, and the remaining bits is actually considered as your tech bits. So this is so once you have that, you should have the concept that we would use the set index to identify which set in your cache should you access the data. And then in the meantime, they will compare the tag on both sides to figure out if it's hit or not. That's how we do it in hardware. But on your end, all you need to do is that you probably need to maintain some kind of table saying that, well, for this set in particular, that we have this 2 or a few data blocks with this prefix tag in mind, right? So that's what we have. So this is a processor called NVIDIA Tegra. So in this class, we have been using an advanced version of the NVIDIA processor called Orin for the simulation. However, no matter what generation they are using, NVIDIA never fixed the problem of conflict misses because they only have 4-way set associativity. So also, right, if you see this, right, for these pieces of a code, no matter you are using the Tegra X1 or Orin, the Orin basically have the double size of the capacity, right? This piece of code is still going to have 100% of misses. So you would know most of the misses of running these pieces of code on NVIDIA processor is pretty much because of conflict misses, nothing to do with the capacity, right? And there is always the first compulsory miss when you access a block. So to fix this, right? So to fix this, right, you have to, so once you figure out the cause of your cache misses, then the remedy becomes crystal clear. So for compulsory misses, it's just because the block is not in there the first time I access it. So several things that you can do, right? So the very idea is that can we carry as many stuff as possible once so that the later access won't miss it, right? So prefetching is a software programmer can do idea. And on the hardware side, you can definitely make your block size larger, but it also costs more and also make the fetch time longer. So most of the hardware, they don't do it. And in addition to prefetch, there are some other things that you can do. So for example, can you change your data layout, right? So for example, if I can arrange my table in a way, for example, one of the demo we have is row access and, well, sorry, not row access. The row store versus column store, right? Most of the database tables, we do the column store because then we condense all the memory items within a single block. So then it means that the amount of compulsory misses would be reduced significantly, right? So that's one way of doing it. Or you can do a condensed layout. So in your assignment, you have learned that if you can change the order of your struct, then it would make your total amount of data being smaller, which reduce the chances of fetching more block, right? So those are the software mechanisms that you can do to improve the compulsory misses. And for conflict misses, it's due to insufficient block within the target set. So the hardware solution is that you just add more associativity, right? So, you know, like people in NVIDIA, they are not idiots, so they definitely know that. But this is not an easy thing to do if you don't have a good fab that can manufacture that chip. So that's why I'm saying Intel has the advantage because its fab is actually doing the best for SRAM storage. So that's why its cache can have crazily amount of weight set associativities, but their competitor can't. But let's set it aside. If I have to work with NVIDIA or AMD processors, then what we have to do is to be creative about how can we make the access pattern more friendly to limited weight associativity. So a few ideas that will work, like tiling, not only can help reduce the memory footprint, but it can, if you do it right, you can also make it small enough to not having the conflict misses. And you can also change the stride of access patterns. So in your assignment, we have been changing the stride to make sure that we are not meeting those conflict misses. And also split the workload, split the loop to work just a few data structures instead of all of them. That's called loop fission, right? Okay, talking about capacity misses. This is the myth because of the working size surpass the capacity. So a lot of people do not have a clear idea about the working set size, what we are talking about. So when people, so that's why working set is a very big, it's a very interesting thing that I don't, in this class, I keep saying that the working set size has different meaning in different contexts. So if you talk to machine learning people, or if you talk to some like operating system people about the working set size, they probably would tell you the total memory footprint throughout the whole execution time. But really, for computer architects, we only care about a window period of time. And in particular, for the cache problem, the working set size should be be considered as the last time I visit a block and the next time I visit a block, how this is the window time. And between this between these two times points, how many blocks of data that I have visited. And if that total amount surpasses the cache capacity, that's when we can finally code there is a capacity miss. And of course, several things that you can do to minimize that working set. For example, if during every window period of time, you make sure that you are only working on a small tile of your matrix or small tile of your array, that's basically reduce the working set size. Or you can ultimately make your data set size small. For example, condense the data structure, and some of crazier ones like I can have compression. I can have exclusive or stored data, right? So those are the crazy things that I don't talk about. Okay, so but the thing is that in our computer system, memory is not just that simple in a way that we want to accommodate the demand of concurrent execution of multiple programs. So in fact, the memory address you see from your processor are not a real memory address that you would access in a memory, because the operating system created an illusion called virtual memory. So the virtual memory is in a way that when you execute your program, the operating system will create an illusion called process. And a process is essentially a virtualized computing resource plus a virtualized memory. And by virtualized computing resource is that every process would think I own a whole processor. And every process would think I own the whole memory space. So how do you manage those is that you have to do fine-grained or some sort of coarse-grained multiplexing of your hardware resource. And that's what you will learn called context switching or mode switching in your, context switching in your CSE120. And on the memory side, they would do virtual memory to support that. So the virtual memory is basically trying to encode your, trying to make the virtual, trying to compile and label your data on the virtual address. But what would really happen is that we would dynamically map those virtual address into physical memory location when we are running them. And the resource sharing is first come, first serve and on demand. And whenever we are lack of space, we will pretty much simulate, we will pretty much doing a similar things as we have done in the cache is that we kick out the least recently used page, and so that we can accommodate all the data that was in demand. So the approach that has been taken in the modern operating system is basically like virtual memory code, like demand paging plus swapping. So if you are interested about this, take CSE120. But that set it aside. On the architectural side, the problem that the virtual memory abstraction actually took to us is if you want to faithfully translate every virtual address to a physical address, you need a huge table that would never be reasonable in modern architecture. So it turns out what happened is that modern architecture used the so-called hierarchical page table that use a B-tree structure to index all the page table leaf nodes. And based on that, it really creates a problem that whenever we need to figure out the translation between a virtual address to a physical address, you have to go through several DRAM accesses. And the worst case scenario, it would take 10 times. So if you have to ever translate an instruction address plus the data address that it accesses, it would take about like 1 microsecond at least to make it happen. This is terribly slow. So turns out modern processors, they all have this spatial cache called TLB. The TLB is not BLT. It's a spatial buffer that caches the translation of virtual memory and physical memory addresses. And by addresses, it's not a full address. It's just the virtual page number and the physical page number, because the offset bits is not necessary to translate. However, if you put TLB between the cache and the processor, you just make the access time even slower. So we are not going to do that. So the most common solution right now is actually doing the so-called physically tagged virtually indexed cache, in a way that we notice that the page offset remains the same before and after translation. So what we want to do is that in the meantime, we can access the physical tag, but also perform the translation. So if you could make your virtual page number equal to the tag of your physical cache, then once you figure out that translation, once you fetch that tag, compare, you would know if it's a hit or not. And the trick here is that mathematically, we know the block offset and set index, the page offset, we never translate. So if you could have make your set index and block offset to be exactly as the same size as your page offset, then you can exactly use those virtual address to access your cache. However, this put a constraint in our cache design is that your log b plus or log s has to be exactly to be log of your page size. So that's why we always see the L1 cache has a very limited size if we want to fulfill the demand of virtual index physically tagged the cache. And then another thing that we want to, so after we address the whole memory problem with caching, with better code, with TLB, as we learned from MDOS, the moving target now goes back to the processor itself. And for the processor, the processor design affects a few things. First of all, the CPI of executing instructions and the cycle time of executing an instruction. So the very first thing that people would typically want to do is that, can we reduce the cycle time? So if you want the processor to do everything within a cycle, that's actually taking a very long time. So then modern processors, they all incorporate a design called pipeline execution. So what that means is that every cycle and instruction only perform parts of the execution job instead of the whole thing. So what does that mean is that an instruction has to execute for multiple cycles before it can finish. However, the good thing is that because each cycle, we only use part of the circuit in the processor. So once we are done, we put the data, temporary data in a pipeline register, which will be propagated to the next stage at the next cycle. And after we are done that, the circuit is ready for another instruction to use. So if you take a different view of the execution stage, you will figure out that if you have sufficient amount of instructions in the processor, at any moment, you are going to see every pipeline stage would deal with a different instruction and multiple instructions that can be executed in parallel in this processor. And although each instruction would take more cycles to execute, but if you pay attention to the throughput of executing this instruction, every cycle we are indeed finished one instruction. So you're still going to enjoy the same CPI as a single cycle design, but your cycle time is a lot lower. So pipelining is basically a mechanism that uses instruction level parallelism to improve the cycle time. However, is it always the case that we can use the pipeline as what we want without hurting the CPI? The answer is no, because for the pipeline is indeed an approach hurts the CPI because we have three different hazards that would make the continuous execution of the pipeline instruction impossible. Those are structural hazards, meaning that two instructions are competing the same hardware resource. Control hazard means that we cannot continuously fetch new instructions because we don't know what to fetch. And data hazard, meaning that an instruction cannot be executed right now because it's waiting for another result from others. So to work around this pipeline hazard, several approaches. So for structural hazard, there's not really the software programmer can do. On the hardware side, you can either stall, you can either provide more read-write ports, or you can split the hardware units. And the most common design we will see is that we always see a split instruction and data cache because we want to avoid the structural hazard. And for control hazard, if you take a look of the latency of control hazard, and we have been showing you in the class how to measure that. Basically, take the same code, and if that code, the query of non-sorted data and the sorted data, that's the example code that we have. So the main loop itself has nothing different in their the amount of computation, and memory accesses, right? And the memory access patterns are all the same, right? So if you see any performance difference, it must because of the branch behavior is different. So by comparing the performance of unsorted data and sorted data, you will get significant different amount of number in branch misses. And by doing that, you will be able to evaluate roughly how much cycles on average a branch misprediction will cost. And our conclusion is that for an Intel processor, it would be 34 cycles, which is pretty long, right? Remember, for memory accesses, it's just like 50 cycles, right? So this is too long if we have the cache doing perfectly. So turns out our solution is that we need to have a branch predictor. So modern processors, we would take different approaches in branch prediction. The most common, the most easiest one, but we don't use it a lot, is just a simple 2-bit predictor, is that we have a saturate counter to see what's the last 2 outcome of this branch. And typically you can for this one, if for particular branch instruction, if it take for consecutively the same direction for twice in the past, then that would change your branch prediction. That would definitely change the direction you are going to predict. So that's the basic idea of that. And with that, you can see for a regular loop, it's doing very well. However, if today I add more flavors into the loop with an if-else statement, then you will figure out that this is not doing very well. So to accommodate a different type of loop, which is also frequently occurred in your code, then we have the global history predictor, or say the two-level predictor. So why we call it two-level predictor is because the first level is the global history register. You have to use this global history to index the branch that you have. So this predictor takes a longer time to train, but as we later learned, this will work perfectly for this code when we need to when we still sufficient amount of iterations. And however, as we also learned, is that none of the predictor is perfect. So if you have the space, for example, Moore's law now allows you to add more stuff in there. Why don't we just make the branch predictor more complex? So modern processors, they all have so-called a hybrid predictor design. So for example, the simple idea is like having a tournament predictor, which we have both local and global, and we use a predictor to predict which predictor will give you a better prediction, right? So that's the basic idea of tournament predictor, right? So it's a two-level approach, and you know, like you can also use like the idea like neural networks to make a branch prediction, and in fact, modern AMD and Samsung processors, they incorporated this design. So, but don't forget the big idea here is that the branch prediction has 3 different categories. Like a local predictor is based on each branch behavior, because it believes the branch behavior has no relationship with other parts of the code. And the second one is called global history. So it works well for the case where you have correlation among multiple different branches. And this is not something a local prediction can capture. And however, you know your code is always a mixture between these 2 behaviors. So if you only have one, it's not going to work. So that's why we introduced the concept of hybrid predictors. So if you revisit these pieces of code, right, you will figure out that the local history of the first, and sometimes we want to see if one predictor is better fit for this pieces of code or not. Then it doesn't hurt that you try yourself to see what's the local history of each branch. So for example, for this pieces of code, if you take a look of this local history of each branch, for branch X, it's always swing by taken or non-taken. So if you have heard about what I said, the local predictor only changes the prediction if I see 2 consecutive consistent results. So what does that mean is that if there's no 2 takens back to back, I'm from the same branch, I'm not going to ever change my prediction for this branch. So what does that mean is that if you have a 50-50 and it alter once again, then what does that mean is that the local predictor can never do a good job on this kind of branch. However, for the global predictor, if you can write down the whole thing in a different way, like by putting this two stuff together, then you will figure out that there's a clear pattern. Like for this example, there is a 4-bit pattern that a branch, the global history can potentially capture, right? So sometimes if a question asking you about would global predictor do a good job on this piece of the code, or would local predictor do a good job on this piece of the code, write down this table, then you will probably figure out something. And so another example that you can do is like, okay, for this pieces of a code, it's super clear, right? Like for the branch X, right? You will see that, well, it will consecutively non-taken for 9 times, right? So you will know if, even though I initially predict taken, however, after the 3rd time, I will change my prediction to non-taken. So I would at least get this part right, right? And however, for the global predictor, you will find out, well, the history of making everything perfect is so long in a way that I could never get this right, right? So then you would know the global predictor is not going to do anything better than the local predictor. So it doesn't, so at this point, right, if you really want to make this prediction perfect, you need a very long history. But it doesn't worth you to do that because the local predictor can do better. So this is another justification why we want a hybrid predictor instead of the just the local or global predictor. And in fact, as I said, because your code exhibit all kinds of behavior, so that's why all these predictors that we mentioned in the class, they always has this. However, as a programmer, I don't need to worry about the hardware design. In fact, I have to know what kind of programming behavior would let a processor easier to predict. So if you have a piece of code like that, right, then you can figure out that, well, if I have random data inside this array, if I take a look of the the real branch pattern, then you will figure out no matter what threshold value it is, there is no really very regular pattern that the branch predictor can predict, right? So that's why if you have unsorted data for the later loop, it's always going to be bad, right? However, if you can sort it, then you will figure out, even though you have a very simple 2-bit local predictor, you can get 100% hit rate, right? So what does that mean is that if you want to deal with the control hazard, on the hardware side, there are already branch predictors. On the software side, knowing that you have branch predictor, as a programmer, you should try to sort your data or doing something to make your code more easy to predict. Or even better is that how can I just get rid of all the branch predictions? So for example, if you can use lookup table, use lookup table. If you could use use loop on rolling, use loop on rolling, right? However, there's also a trade-off here is that for lookup table, be careful about that. Sometimes the lookup table, if it causes additional cache accesses too many, if it causes too many additional cache misses, then or cache accesses, then it's probably not going to be faster. Because even though you have a cache hit, it still takes 5 cycles, right? So if your code already have a pretty decent branch prediction rate, don't bother doing lookup tables. So now, the last thing in terms of pipeline hazard is the data hazard. So for data hazard, the best solution that we have been talking about in class is not the one that the computer organization textbook would tell you. Computer organization textbook only tell you, well, we should do data hazard. We should use like hazard detection, very complex logic to do data forwarding. But I also show you the best you can do in data forwarding is just shorten the latency by 1 cycle, right? However, given the length of the modern pipeline, that 1 cycle doesn't help a lot. So the best way to figure that out is that, first of all, right, the source of data hazard is because we have data dependency. So if you could try to write your code that doesn't have that many data dependency, would eventually solve the problem. However, there are always cases that we have to deal with data dependency, right? So then turns out if you try to see what we can potentially do, there are a lot of creative solutions. So for example, while loop unrolling is helpful, several reasons, not only because the loop unrolling can avoid the control overhead, but in fact, if you can unroll the loop, then you will find more reorganization opportunity in a compiled code. However, this requires the fact that the compiler has to be 100% confident this is going to happen all the time. So most of the time, compiler won't do this. However, there is some, the hardware has the opportunity of doing this because the hardware can use branch prediction to know if the loop is going to be taken or not taken, right? So turns out the solution the hardware provides is actually using a mechanism called register renaming. So the basic idea of register renaming is that whenever we have a new output, we store the generated value in a in a physical register. And as you can hear here, we have two different types of register. Architectural register that are the ones that the programmer, the assembly language would see. And the physical register, the real value storage that we use internally in a processor to get rid of the non-alias, the false dependency problem. So once we use the register renaming, we are able to schedule our instructions based on their data flow. So an easy way to know what's my code's performance on an auto execution core is using this data flow analysis. So what you would do is that every time when you get an instruction renamed, figure out a few things. First of all, if the data dependency is resolved or not. If it's not, then figure out when can we address it. So for example, right now I have instruction 1 coming in. I know instruction 1 is the first, so there's no one is depending on. And when the instruction 2 comes in, I examine the data dependency of that. And I figure out at this moment, there's no one competing it. And another thing to be aware about is the issue with, which means the capability of using the hardware. And for this particular example, we are assuming issue with 1, which means for any cycle, we can only have at most 1 instruction being in either memory, LU, or BR execution stage. And now looking at instruction 3, you will figure out instruction 3 is depending on instruction 2. So based on our policy, we would schedule an instruction based on the order of the instruction itself. That's one of the policy. So what does that mean is that if when 3 is available, that would be the first instruction we execute no matter what. So then what does that mean is that 5 cycles after, you are definitely free to execute this instruction 3 if no one else is competing with the memory, right? Same thing for instruction 4. So this is how you put a scheduling, right? For instruction 5, as long as the LU is available, we can use it. However, for instruction 6, that's when we are going to deal with the limited issue with problem, because the next 2 cycles we already scheduled instruction 3 and 4. So if you use this policy, you will figure out at some moment, because we have the capability of auto order scheduling, every cycle we would be able to execute 1 instruction from the loop iteration, which means that you are going to have a CPI equal to 1, fully utilize this 1 issue pipeline. However, the current execution flow is still not ideal because we noticed that for multiple functional units, they are still idling during the whole process. And in fact, there are chances that we can execute instruction earlier if we could have the instruction being renamed earlier. So it turns out that's why we have the idea of superscalars. And the superscalar is basically saying that we give the processor more capability to fetch more instructions and issue more instructions at the same time. So now your CPI would be 1 divided by the minimum of your issue width and your fetch width. So saying that if you can fetch 2 instructions at the same cycle and issue 2 instructions at the same cycle, for the same program, now we are able to bring down the CPI to 0.6 instead of close to 1 as what it originally says. And this design didn't add any more functional units. And in fact, however, even though we have the best processor, if you write your code in a very bad way, like if you heavily rely on some of the linked list based structure, well, this is a very complex program. Okay, so what is this? Okay, so like if you have a linked list program, right, what will happen is that because we have a critical operation that determines the execution time, pretty much the current equal to current next, and knowing if current is equal to null, this chain, right? So then this chain would determine all the performance, and no matter how wide issue you have in the processor, you're not going to fully utilize it. So a high-level guideline is that you should never write code like this, right? So in terms of data hazard, several things we can do, right? Dynamic instruction scheduling on the hardware side, but on the program and compiler side, real-time instructions use equivalent statements with fewer data dependency, or even change your algorithm that make it less data dependent. And we didn't spend a lot of time talking about the pipeline that you have in the textbook, because most of the modern processors, they don't have the 5-stage pipeline that the textbook tells you. Instead, they have the pipeline that I show on the slide. So for example, this is the Intel processor, pretty much similar to the pipeline that we have in a slide. And this processor is actually having a 12-issue processor with 5 on LLUs, 7 on the memory. Even for their WinP cores, they still have 5 issue. And for AMD processor, they should have at least like 8 issues. So you can pretty much assume that we have wide issue processor all the time. So don't try to write code like linked list that would underutilize this hardware. For then, this is a set of code example to tell you about how to optimize a program on modern processors. But through this 5 different implementations for the same pieces of code, we have seen from the first one to the second one, we do something like loop unrolling. And in fact, the compiler can try to do some reordering in the code. And from B to C, we are basically utilizing a lookup table to avoid a data dependency in this chain of computations. So this is an example how we use lookup table to reduce the data dependency in the code. And for D, we finally try to demonstrate an example how to automatically get rid of the control hazard, right? And for E, it's the worst example, which tells you don't do that, right? So the slide that previously I demonstrated, we have some issue in a critical path analysis, and then I figure out for the version A, here is a shift right instruction, and in a compiled code, we didn't notice that, but for x86, they are really annoying in a way that they have different type of representation of the same register. So in instruction 1, you see there is an EAX, right? So the EAX is actually the 32-bit version of AX register. And RAX is actually the 64-bit version of the AX register, but they are physically the same. So what does that mean is that there is a hidden data dependency between 1 and 4 and 4 and 1. So with that taken into account, your dependency chain will go from 1 to 4, 4 to 1, 1 to 4, 4 to 1, right? So that's why it's taking 2 cycles per iteration on average. However, if you could have loop unrolled your version B, what turns out is that you still have the dependency chain, but don't forget this dependency chain is for 4 iterations at a time. So even though it takes 4 cycles, but it's 4 iterations in each of the dependency chain. So the average CPI is actually twice of half of the version A, right? So with version B, that's what we see, the completely loop unrolling. So this summarizes the optimization that we have done for these pieces of code. But if your instruction already provides some facility to do hardware acceleration, use it would give you the highest efficiency. So here are the tips of programming on modern processors. Don't forget about optimizing the cache memory locality first, and then branch, and then talking about how we can see if there are hardware acceleration options. So, however, if some people insist to use code like linked list for a few reasons, then there are always cases that we are not going to fully utilize our processor. So the concept of simultaneous multi-threading is actually using the concept of thread level parallelism to fully utilize your processor resource to improve the throughput for the whole system. And so for parallelisms, we can pretty much see there are several types of parallelism that this course introduces. So for instruction level parallelism, which is the capability of executing multiple instructions in parallel. And when we say multiple instructions, this is specifically talking about multiple instructions from the same thread. So it's the same program, the same thread. So it means, like pipelining, register renaming, auto order execution, superscalar, they are all for this. And for thread level parallelism, like simultaneous multi-threading or multi-core processor, we are trying to parallelly executing multiple streams of instructions. They are from different threads, different programs. This is called thread level parallelism. So, and to support thread level parallelism, simultaneous multi-threading and multi-core processor, or say chip multiprocessor, is the solution we took. But through the practice in the class, we know there's no optimal solution for running multi-program workloads. So it turns out modern processors typically have both. And supporting parallel programming, the most important thing is that from the hardware side, we have to deal with the imagination from operating system people, software people. So it turns out we have to make our cache coherent and consistent. However, even though we can make the cache coherent, there is still non-determinism in your processor and in your operating system in a way that the processor clock frequency does not always the same. The scheduling of your operating system is hard to control. So it turns out we would never be able to, we would seldom, rarely, like very, very low percentage of the time, we are going to get an output we want. Most of the time, you are getting like output like 1, 3, and 4 when you are executing these pieces of program. And additionally, because you have to maintain the cache coherence, so there will be a problem called coherence misses. So that's why we have 4 Cs instead of 3 Cs. So so that's another issue we have to deal with. And even though we have our cache coherent, there are still issues called consistency. Means that multiprocessors, they don't have an idea what other people are doing. So it turns out we reorder instructions on our own. There's no agreement. So that's why we are seeing these 4 outputs are possible. But based on the non-determinism of our program execution, even though we desire to have 4, but in our demos, we never see 4 in the very beginning. But it's possible, so that's why I still list it as an answer. And the one that gives us the most bizarre is actually 0, 0. But turns out this is just because the compiler or the processor has auto-order scheduling capability to make it wrong. So the solution is that you should use memory fence. And you should remember, after our demo, the memory fence will prevent us seeing 0, 0. And sometimes we will see 1, 1. However, we are still seeing a majority of 1 zeros and 0 1s, and there is no this is very unpredictable. So that tells you parallel programming is very, very difficult. So because parallel execution on homogeneous processors are so difficult, people try to find other alternative ways. For one of the execution models is called vector processing model. So the vector processing model is basically every time each instruction or each operation, we take the whole vector and when we want to perform computation, it's also one instruction performed uniformly on every element within a vector. So in this way, there are several benefits we can take. First of all, you can parallel the execution on multiple ALUs at the same time, but also save the overhead of controlling all these ALUs because it's just one instruction. So you can reduce the instruction count, you can reduce the hardware logic to control these ALUs. So this essentially becomes the fundamentals of GPU architecture because graph rendering requires a lot of vector operations. And so turns out this is another type of parallelism in our processor now called data level parallelism. So data level parallelism is presented in either GPU architecture or SIMD instructions in your CPU because modern processors, they notice that, well, we still have the demand of doing this on CPU. So that's why they added there. So then finally, last lecture, we talk about dark silicon problem. And in fact, the demand of AI ML application, we want higher speed, higher performance. However, because of the dark silicon problem, we would never use them at the full speed. So it turns out we need to have a lot of workaround, for example, using the same transistor to generate, to place a lot of slow processors. And based on the MGAUS law, we know even though they are slower, but as long as we have more, we can still get better performance. However, there are always cases that we need deadline-driven applications. So then turns out this is not the ideal solution. And in fact, sometimes if you slow down the performance and if you cannot speed up, you cannot reduce the power consumption sufficient enough, you are going to get more energy consumption, which is eventually bad for your cost. So it turns out there's never an ideal solution in just a homogeneous processor design. So we explore heterogeneous processor design like big little cores. Or you can be more creative by using hardware accelerators, which we figure out what's the most important computation kernels we want from the programs, the application domain we want, and we spatialize the circuit. So then we can reduce the area required for the core algorithm, and we can further pipeline it so it can still be parallelized. And if the algorithm itself implicitly is parallelizable, we can actually duplicate more within the same area to make better area efficiency, better power efficiency. So the famous example includes Google's tensor processing unit. And turns out, if you pay attention to modern processor design, it's all a collection of general purpose cores plus hardware accelerators and vector cores. And this is true for Intel processor, Apple's processor. So the landscape of modern computers always include the conventional monomer architecture. Don't forget, that's the high-level view, but also other accelerators as the modern processor view. So so in conclusion, why we care about this class, because we are now in a so-called dark silicon era, and single core isn't getting any faster, multi-core doesn't scale anymore. So as a programmer, in the future, I mean, algorithms are still important, but can we be more creative looking over the hardware functionality and tailor our algorithm to leverage more of the hardware units? A few announcements before you leave the classroom. So first of all, course evaluation, you can use that to replace your lowest performing reading quiz. Assignment 5 due tomorrow night, but I will release the solution tonight because I know a lot of you are taking final tomorrow. So tomorrow when you wake up, check the assignment solution. And I mean, I don't mind if you guys get 100 in your assignment, right? So, but I do want you to be better prepared for your final. So check the solution tomorrow when you wake up, and check your grades on Saturday after AMN. That's more likely the time I get a better resolution of your final scores. And the final exam should be tomorrow sometime at the Trident Testing Center. I won't be there, but I wish all the best luck for you guys. Some of you ask about what the average of the midterm, and I'm not a big fan of doing that, but if you want to have an idea about how much more better I have to do in my final. If that helps you, that motivates you, that's the only reason why I put it up here. And again, don't forget, what really determines your final grading is not a single item, but a synthetic result of your final, midterm, reading quizzes, participation, as well as assignments, right? So what I do is that I would typically looking at your total and then rank. And based on the ranking, sometimes like significantly you will find a gap here, right? Because I hate people argue with me like, what can I do to get a better grade, later grade, right? So it turns out I would typically cut off the threshold at this kind of places. So I will typically respond to you, well, you have to get 20 more credits in your final to bump up. So don't bother doing any regrading, right? So save our time. So based on the current projection, if you are at this part, you are probably going to get an A+. And if you're lower, if you right now you're between 80 and somewhere like I believe this is 75, then it's a projected A. And then if you are above 70, right now you see there's a huge gap here, right? So that's why we are going to separate A- and B+ here. And then there's a group of Bs. And now you know the end. I don't know what happened to this group of people. But if you are still enrolled, you know you have a lot to do in your final to make that up. But other than that, this will probably give you a good idea about what the roughly grading would look like. And again, like if everybody is really close that I cannot really find a gap like this, I'm happy to give everybody something above 8B+, right? But it's never the case. But you can change it. So other than that, enjoy the rest of your summer. And hopefully, when the next time we see each other, you are happy seeing me. I will happy seeing you. Other than that, I don't know if we ever have a chance in the future to cross by each other, but if one day we cross by each other on campus, in company, somewhere, or even when we are travel, we can call each other friends. I will hope you enjoy your summer, enjoy the pizza, and see you in the future. Yeah.